Welcome back to New Findings of the Universe. Today, we're focusing on 3IATLAS, our newest confirmed interstellar visitor. I'll keep this formal but friendly, and I'll walk you through what's genuinely new without the fluff. In short, we've gathered better measurements of its brightness changes. We've refined its path through our neighborhood, and we've learned more about what its light tells us about the dust and gas around it. Interstellar here means that I-SEN-T bound to the Sun, its trajectory is hyperbolic. So this is a traveler from beyond our solar system. That alone makes every data point valuable, because it lets us compare how worlds form around other stars with what we see at home. What's new starts with monitoring. Multiple observatories are now tracking the object across wavelengths, optical for reflected sunlight and gas emissions, infrared for warm dust, and in some cases, polarimetric observations to probe grain properties. The cadence of observations has improved, which means we can separate real behavior from one-off measurement noise. We're seeing that 3IATLAS is active. It vents gas and dust, building a coma and tail the way a comet does. That activity level appears to fluctuate, likely because of rotation, sunlight-driven heating of different surface patches, and possibly an irregular shape that exposes fresh ices over time. We've also seen modest updates in its orbit solution. As additional astrometry comes in, orbital parameters tighten. That matters, because small errors early on can shift predictions by millions of kilometers later. The current path confirms the object is incoming and outbound on a one-time visit. It 1T loop back like a long-period comet from our Oort cloud, for a field hungry to compare foreign materials. This is prime time to point our best instruments before 3I Atlas dims and disappears into deep space. One more What's New angle is comparative context. With Oumuamua and 2I Borisov as our two prior interstellar benchmarks, we now have a third data point. 31ATLAS looks more comet-like than Oumuamua, more like Borisov in that sense, but the details matter. The gas mix, the dust grain sizes, how quickly activity ramps with sunlight, and how color changes with distance from the Sun. Those measurable differences begin to answer a big question. Are exocomets broadly similar to ours? Or do they carry signatures of their natal systems that we can read from afar? Let's recap the story so far in plain terms. 3.1 Atlas was identified on a path that flags it as unbound to our Sun. Follow-up observations pinned down that hyperbolic orbit and confirmed. We weren't looking at a peculiar long-period comet just skimming by. From there, teams shifted into characterization mode. Track its brightness, take spectra when possible, and map how its appearance changes as it approaches the Sun. Early photometry showed it brightening in a way consistent with cometary activity. Sunlight warms, surface ices sublimate into gas, gas drags dust, and the coma grows. That's the engine behind the classic fuzzy look. The rate of brightening, though, is where things get interesting. Some comets brighten smoothly, others brighten in fits and starts. 3.1 ATLAS has shown variability that hints at rotation and perhaps patchy active regions, the same way a lumpy snowball displays different faces as it spins. Spectroscopically, observers have been hunting for familiar cometary gases, cyanogen bands, possible CN, and broader color trends that hint at larger molecules or dust-dominated light. The mix tells us about surface composition and processing history. Even upper limits help, because a non-detection within a given sensitivity range rules out certain volatile abundances. Meanwhile, polarimetry, measuring how light is polarized after scattering off dust, adds another layer by constraining grain size and texture. Coarser grains and fluffy aggregates polarize light differently than compact fine grains, and those differences point back to formation and subsequent thermal processing. On the orbital side, each new measurement reduces uncertainty. That's how we refine predictions of when it is closest to the Sun and to Earth, and how we plan the best windows for space telescopes and large ground-based mirrors. If you're wondering if it will become a naked eye spectacle, the short answer is that's unlikely. Interstellar visitors tend to be modest, but modest scientifically can be gold, because it lets us see a genuine sample of extrasolar building blocks in action, how they hold ice, how quickly they shed dust, and how sunlight sculpts them as they pass by. Hubble's value here isn't just sharp pictures. Stable, repeatable imaging with well-understood filters that let us compare like with like as the object changes. High-resolution images help separate the central condensation, the unresolved core plus dense inner coma from the fainter outer coma and the initial lines of the dust tail. With Hubble, we can also better assess the coma shape. Is it symmetric, or does it show jets, fans, or a preferred direction that matches a rotational pole? Another advantage is that Hubble-S filters can be paired with ground-based spectra to triangulate what we are seeing. If a certain emission band brightens and Hubble's imaging in a nearby filter also shows a localized brightening region, we can infer where gas is most concentrated and whether dust production is peaking simultaneously. That spatial information turns a simple "it got brighter" into this patch on the coma is changing faster, suggesting a local source region. Hubble's point spread function and low background also help in measuring the dust distribution more precisely. For example, the brightness fall off with distance from the nucleus. How quickly the coma fades depends on outflow speed, dust production rate, and radiation pressure that pushes fine grains downwind. If images across several days show the fall-off steepening or flattening, we can infer changes in outflow regime or grain size distribution. That, in turn, feeds back into estimates of how much dust mass the comet is shedding and how that correlates with gas release. Finally, there's the subtle but critical discipline of astrometry, using Hubble images to pin down the object's position with very high accuracy. Those points tighten the orbit solution. Even a small improvement in the orbital elements can change where we point other telescopes later. And it reduces the chances of systematic bias in interpreting activity. In short, Hubble provides the crisp baseline imagery that makes the rest of the campaign more reliable. When JWST is in play, the conversation shifts to infrared sensitivity and spectroscopy with exquisite detail. For an active interstellar comet, JWST has two superpowers. First, it can see thermal emission from dust, grains telling us their temperature distribution and seismics. Second, it can capture vibrational bands of key molecules in the near and mid-infrared that ground-based telescopes can struggle with because of Earth's atmosphere. Infrared images let us test how far the dust halo extends and whether there are multiple dust populations. Warm, small grains glow differently from cooler, larger grains. If images at two wavelengths show different coma profiles, we can infer how radiation, pressure, and grain dynamics are sorting the material. That's crucial because dust is the delivery system that carries the surface story out into the coma where we can read it. On the spectroscopic side, JWST's instruments can search for substances that tell us about formation, temperature, and history. Certain organics, water-ice signatures, and CO-CO ratios are sensitive to where in a protoplanetary disk a body formed and how it has been baked or altered since. 3I Atlas shows a volatile mix notably different from ordinary comets in our solar system. That bolsters the case that planetesimal formation chemistry varies a lot between stars. It looks surprisingly similar. That might mean disk physics converges on common recipes more often than we expect. JWST also helps with time domain behavior. Watching the object over multiple visits lets us see if activity spikes at particular longitudes on the nucleus, clues to rotation period and the distribution events. A subtle brightening at infrared wavelengths, without a corresponding jump in optical light, could mean we re-seeing dust production without a big gas signal. Or it could mean larger grains are being lofted more efficiently than expected. Those small mismatches push models to evolve, and that's how we move from pretty spectra to physical understanding. We don't have a resolved picture of the nucleus as a solid body, but we can infer shape from indirect clues. Light curves that show repeating ups and downs suggest an elongated body or strong jets anchored to specific longitudes. If polarimetric measurements vary with phase angle, the angle between Sun, comet, and observer it can indicate anisotropic dust outflow tied to particular surface areas. Jet morphology in images is another proxy. Fans or narrow jets that maintain a direction over many hours hint at fixed source regions and a stable spin axis. If the jets appear to sweep like a lighthouse beam, that motion encodes the rotation period. Combine that with the curve of the dust tail, and you can back out constraints on the obliquity, the tilt of the spin axis relative to the Sun-comet line. Why do we care about shape for an interstellar comet? Because it connects to strength and history. A very elongated nucleus might be a contact binary pair of smaller bodies that merge gently, or a fragment stretched by thermal cracking and passed out gassing. A more compact shape suggests different formation or processing outcomes. Shape also controls how sunlight is absorbed and re-radiated, which patches heat first, and where stress accumulates as volatile pockets thaw. All of that, in turn, influences how activity ramps and whether the comet is prone to shedding larger chunks. Finally, shape ties back to Oumuamua. That first interstellar object pulled us into debates about extreme elongation versus unusual outgassing, with 3I Atlas showing more classical cometary behavior. Any independent constraint on its shape helps us understand whether Oumuamua was a rare outlier or a part of a broader spectrum of interstellar body geometries. The tail is a laboratory for forces. Radiation pressure pushes small grains away from the Sun. Larger grains lag and form a broader, more slowly curving structure. If we separate the ion tail made of charged particles accelerated by the solar wind's magnetic field from the dust tail, we learn two different stories at once: the immediate gas chemistry and the dust dynamics. In images, a straight, narrow, bluish tail often marks the ion component, aligning roughly with the solar wind's magnetic field lines. A broader, yellower, or whiter tail is dust-bominated, curving along the comet's path as grains feel both gravity and radiation pressure. Measuring the angle between these tails and how their brightness changes over time lets us estimate gas production rates, ionization conditions, and the mix of dust sizes being launched. Embedded in the tail, synchrones and syndonize the mathematical families of dust release times and sizes can be modeled to match observed structures. If a distinct feature appears and then propagates down the tail, it may mark a timed burst of dust release. That timestamp tells us when the nucleus changed state. Tie that back to a spike in the light curve or a spectral change, and the picture tightens. We move from pretty tail to a physics timeline. For an interstellar comet, tail analysis also speaks to durability. How quickly dust production ramps, how fine the grains are, and whether the ion tail is strong give us a sense of how much volatile inventory is accessible near the surface. That hints at whether 3I ATLAs formed in a cold outer disk around its parent star or migrated inward before ejection. The tail, in other words, is a moving archive of that comet's past. Cyanide usually traced via the CN radical in optical spectries, a classic cometary marker. Detecting CN emission bands helps confirm active outgassing and provides a comparative benchmark. Because we've measured CN in many solar system comets, the intensity of CN lines, when calibrated, can be translated into production rates under reasonable assumptions. Why does CN matter for an interstellar comet? Because the abundance of CN relative to water and other volatiles tells us about chemical pathways in the natal disk. Different disk temperatures, radiation environments, and timescales of formation lead to different inventories of nitriles and other organics. If 3I Atlas is rich in CN compared to typical comets, that might indicate formation in a region with more nitrogen-bearing chemistry or with less processing that would otherwise deplete fragile molecules. There's a caution here. Observed. CN strength depends on excitation conditions and how well we can subtract background and separate emissions from the reflected sunlight. Upper limits are still meaningful, and comparing multiple gas tracers is stronger than focusing on one. For example, CN alongside hints of C, or even CO in the infrared would paint a fuller picture. If CN is weak while dust is strong, it could mean the comet is dust-rich, gasper at this stage. Or it could reflect photoassociation rates and viewing geometry. If you're picturing a toxic cloud, don't. We're talking about faint emissions from a tiny gas coma in space. For scientists, CN is a fluorescent signpost, one we can read from enormous distances to reconstruct the chemistry of a body that formed around another star. Polarization measurements tell us how light is being scattered by dust grains in the coma. When sunlight hits irregular particles, the scattered light becomes partially polarized. The degree and angle of that polarization depend on grain size, shape, porosity, and composition. By measuring polarization at different phase angles, we can infer whether the coma is dominated by fluffy aggregates or compact grains. Why does this matter? Because grain properties reflect the comet's formation and processing. Fluffy, porous aggregates suggest gentle growth and limited compaction. Compact grains can point to thermal processing, sintering, or repeated ejection and reaccumulation. Polarimetry complements color measurements. A redder color slope plus high polarization at certain angles often signals larger, more porous grains, while a flatter slope and lower polarization might imply finer or more compact dust. For 3I, ATLAS, polarimetry helps distinguish whether we're looking at a dust population similar to ordinary solar system comets or something that hints at a different recipe. Interstellar visitors give us a rare chance to test whether comet dust is universal, or if it varies in ways tied to the host star's environment. If we find polarization behavior outside the norm, that's a breadcrumb pointing back to its origin. Polarization can also change over time as the comet becomes more active. As activity ramps, newly exposed vents might launch different grain sizes than older, more insulated regions. Tracking polarization alongside brightness and spectra can catch those transitions. Each transition is a kind of tomography, revealing new layers of the nucleus by the dust they release. When people hear turning green, they often think of C emission bands and the familiar greenish glow seen in some comets. Green comes from specific molecules fluorescing under solar UV light. If 3I Atlas shows a stronger green component with time, that suggests changes in the gas mix in the coma. Either more of a given species is being released, or the viewing geometry and solar excitation are boosting those lines. Color is not just aesthetics, it's chemistry and physics. A shift toward green can indicate that certain volatiles are becoming more prominent as the comet warms, exposing pockets of ice that release gases efficient at producing green emissions. However, turning green visually in wide-field images can also be influenced by dust scattering and camera filters. That's why spectroscopy is the referee. It can confirm whether specific emission bands are stronger, while calibrated photometry can sort out whether broadband color changes are dust-driven or gas-driven. In the context of an interstellar comet, a recognizable green signature has two implications. First, it gives us comparative leverage against our catalog of solar system comets. Do the same molecules dominate, or is the ratio different? Second, it feeds back into activity models. Greener means gasser, and gas production and dust production are linked. We can test whether dust-to-gas ratios evolve with distance from the Sun in ways familiar to us, or in ways that differ. Let's address this with respect and clarity. No, the data so far are consistent with a natural comet. A small body shedding gas and dust under solar heating, with a coma and tail that evolve in familiar ways. The interstellar origin is what makes it exciting, not any sign of artificial behavior. Why does this question arise? In part because our first interstellar visitor, Oumuamua, was weird. It didn't show a big coma. It exhibited a small non-gravitational acceleration that sparked debate about exotic explanations. Subsequent work proposed natural mechanisms like outgassing of difficult to detect volatiles or dust-driven effects that could account for it. With 3I Atlas, we're not seeing that kind of anomaly. We're seeing classic comet behavior: gas lines, dust scattering, tails, and activity trends consistent with sunlight-driven sublimation. Skepticism is healthy in science, but the bar for technology is extraordinarily high. A claim like that would require signatures wildly inconsistent with natural processes' coherent radio transmissions. Engineered spectral features, impossible dynamics. Nothing like that is present. Instead, we have a body that fits on the cometary spectrum, with small differences that are precisely what we hope to learn from: composition, grain properties, and activity rhythms that tell us about its home system's chemistry. So let us keep our curiosity where it's most powerful, in using this past to measure, compare, and learn how planetesimals form elsewhere. The real marvel is that we can read the chemistry of another system from a traveler no larger than a mountain, by teasing information out of a faint glow in our telescopes. As 3I Atlas approaches Perihelion, the point of closest approach to the Sun, the stakes go up for observers. Activity typically increases with solar heating, but not always smoothly. Crust can crack, vents can open, and the balance of gases can shift as different ices reach their sublimation thresholds. For us, that means the best window to catch changes is often the weeks around perihelion, when the object's behavior can evolve on timescales of hours to days. Observationally, this is the sprint. Teams coordinate to get spectra across multiple bands, optical for common emission species. Near-eye and mid-eye are for organics and COSO and polarimetry to see if grain properties evolve. Imaging tracks jet morphology and tail structure, looking for new features that mark outbursts or rotational effects. High cadence light curves search for periodic cadence that might lock down rotation period or reveal it more confidently than before. Each discipline feeds the others. The sum is far more powerful than any single dataset. After perihelion, there's the question of survival. Some small comets fragment under thermal stress. Others sail through and slowly fade. If 3I Atlas holds together, we'll have a longer post-perihelion runway to study how activity decays and whether composition signatures change as fresh surfaces are exhausted. If it sheds pieces, that's a different kind of opportunity. Fragments expose interior material, letting us sample a deeper layer of the nucleus's history. The long view is this: every interstellar comet is a message in a bottle from another disk. Approaching perihelion is when the message is easiest to read. The more we coordinate, the more legible that message becomes: dust sizes, gas ratios, rotation, shape clues, and tail dynamics, all spelling out how planetesimals can form and evolve beyond our Sun. When 3I Atlas swings around and heads back to the dark, it will leave us with numbers, not headlines. Those numbers will sharpen our sense of how common, or how diverse, comet physics really is across the galaxy. Thanks for staying with me through this deep dive into 3I Atlas. If today's tour helped you see why this interstellar visitor matters, the chemistry hidden in that faint green glow, the dust stories written into its tail, the way Hubble, JWST, and even TESS each add a piece, then you read exactly the kind of listener this show was made for. As 3I Atlas approaches perihelion, the clock is ticking. Activity can change in hours. New jets can switch on, and spectra can flip the script on what we think we know. I'll be watching the data as it comes in, and I'll bring you a follow-up episode with the best, most reliable results, no hype, just what the measurements actually say. If this video helped you understand better, then subscribe and turn on the notification bell so you won't miss any future episodes. And share this episode with the one friend who always asks great space questions. Your questions shape this show, so send me the next topic you want unpacked. A new JWST result, a puzzling light curve, or the latest rumor you want translated into real science. Until then, keep your curiosity pointed up. Keep your skepticism sharp. And remember, every faint smear in a telescope is a message from somewhere else. We're just learning how to read them better. I'm glad you're here for that. See you in the next episode.